In this example, we are told that Bilbo sets off on a hike from Bag End at a bearing of south 80 degrees west. After 4.2 kilometers, he changes his bearing to south 22 degrees west and continues hiking for 10.3 kilometers. We want to find his distance and bearing from Bag End at the end of the hike. We will round our answers to the nearest hundredth of a kilometer and to the nearest whole degree, respectively. Okay, so what we're working with here, if I draw a picture for this, let's start with the beginning. Bilbo sets off on a hike from Bag End at a bearing of south 80 degrees west. So, I'll make a point that represents Bag End. And if I want to represent south 80 degrees west, I will draw a little coordinate plane at Bag End. And remember that south 80 degrees west means face south and turn 80 degrees towards west. So face south and turn 80 degrees towards west. That will indicate your direction of travel, which we are told is 4.2 kilometers. We are then told that after those 4.2 kilometers, he changes his bearing to go south 22 degrees west. So after he gets to the end of this direction, to this new point, he changes his bearing. So I'm going to make another coordinate plane at that new position. From there, south 22 degrees west will work very similarly. Face south and turn 22 degrees west. So face south, turn only 22 degrees west. And that will be the direction that we go for apparently 10.3 kilometers. Okay. Our goal here is to find the bearing from Bag End and the distance from Bag End. So we want to find this distance here to where we ended up over at the end of this hike, as well as the bearing. Note that we already know that the bearing to the initial direction was 80 degrees. That means the bearing to this new direction, to where we finally ended up, should be an angle measure that I know is less than 80 degrees. If I can find that angle measure on the inside of this very sharp triangle, then I should be able to find what that angle measure is for the bearing. Let's work with what we can for now. Okay, so we have some values presented to us. We have the two side lengths and we have some angle measures. But those angle measures are not the angle measures inside the triangle, or at least they're not the entire thing. But we should be able to use concepts of angle measures in order to determine at least one inside this triangle and move forward from there. For example, this bearing that was from south 80 degrees west to hit this line that is 4.2 length. Note that that means that I have an angle measure from basically a vertical line to this diagonal line. I know that that space, or that angle measure between those two lines, is 80 degrees. If I apply something called the vertical angle theorem, I then can also consider that 80 degrees to be from this vertical, which is parallel to the one where we created the bearing, to the same diagonal. So we know that 80 degrees from the vertical to the diagonal, and that also means that we have 80 degrees from this vertical to this diagonal. It's also 80. The reason why that is helpful is because now I know the angle measure on the inside of this triangle, or a portion of it, because I know that this angle measure here would have to be the complement of 80, which is 10 degrees. With that, the information of 22 degrees here, as well as the fact that the remainder of this angle measure, this obtuse angle, would include the right angle measure that would represent quadrant 4 for that little coordinate plane. I can then consider that full angle measure here to be the combination of 10, 90, and 22. Or if I redraw this picture to clean it up a little bit, I have the length of 4.2 and 10.3, but this angle measure here I can solve as 22 plus 90 plus 10, so that's 122 degrees. And now I have information to work with this. I now have two side lengths of a triangle and the angle measure in between, meaning we're working with now a side angle side triangle, one of the types of triangles that you want to apply the law of cosines with. In this case, if I do use the law of cosines here, because I have an angle measure, I should actually be able to solve for the side that is across from that using law of cosines, which thankfully is one of the values that we wanted. We do want to find the distance to bag end, that far distance from where we started to where we ended. So I want to solve for the value that I have represented with x right now. So let's go ahead and do that. Using the law of cosines, which would normally be a squared equals b squared plus c squared minus 2bc times cosine of alpha, and I plug in values according for this triangle, the side length I'll be solving for is x, so that's x squared, is equal to the other two side lengths squared, 4.2 and 10.3, minus 2 times 4.2 and 10.3, and also times cosine of the angle measure across from the side length that we're solving for, so that would be our 122 degrees. At this point, I only need to do a square root in order to get the final solution here. So x equals the square root of the information above. And I can approximate that to the nearest hundredth as per the instructions. Let's do that with a calculator here. We have the square root of 4.2 squared plus 10.3 squared minus 2 times 4.2, 10.3, and cosine of 122. Since we're plugging in 122 degrees, do make sure that you are in degree mode there. Furthermore, note that the side length we're solving for, since it's across from 122 degrees, should be the largest side length. It needs to be larger than 10.3, but also it cannot exceed the two side lengths added together. 13.02 seems to fit okay. So that's 13.02 kilometers. We have now solved half of this problem, since we now have the distance. If we can find the bearing, then we should be good to finish. In order to find the bearing, if we look at the original question, we are told that 80 degrees is towards 4.2. So we are told this is 80 degrees. We want to find the bearing to this new direction that would get directly to where we ended, meaning we want to find the angle measure here. So long as we can find the angle measure inside of this triangle, this acute angle measure I have represented with theta currently, then we should be able to take that away from the 80 degree bearing and get the one to our new position. So if I want to solve for theta, I should be able to use the law of sines for that now. For the law of sines, if I want to solve for theta, we would then set sine of theta divided by the side across from theta, which is 10.3, is equal to sine of 122, is the other angle measure I know, divided by x, which we now solved as 13.02. Theta would then be arc sine, if you solve for theta, arc sine of 10.3 sine of 122 degrees divided by 13.02. And we can approximate that to the nearest whole degree. Using a calculator for that purpose, we can do inverse sine of 10.3 sine of 122, make sure you are in degree mode, divided by 13.02. That gives me about 42.14, or to the nearest whole degree would just be 42. Meaning that my bearing then would be if I took that 42 away from the original rotation of 80 degrees. So if I do 80 minus 42, which gives me 38, I can now say my bearing from south is from south turn 38 degrees towards west. And that would be my bearing.